Okay, so we're going to get into Chapter 8, Acids and Bases. Okay, I think you'll find that this is a lot of the things that we've learned. Acids and bases might not be the most difficult. Okay, there's a few things that are pretty simple in there. So, and it's a lot of stuff that's pretty familiar to you already. So acids, they have sour tastes. That's how you can kind of identify them. They react with metals to produce hydrogen gas. Some plant dyes change color due to whether it's an acid soil or it's a basic soil. You can grow your flowers different colors that way. Okay. Bases are bitter, so they're kind of almost the opposite, right? So acids are sour, bases are bitter. They're slippery, and they are also corrosive like acids. So we actually use bases when we want to clean out our sink. We dump Drano down the sink. That's a strong base that we're dumping down the sink. Okay, we don't dump the acid down the sink, although it would clean out your drain as well, because the acid also reacts with metal, which produces hydrogen gas, which we don't want bubbling up into our house because we have a metal pipe somewhere. So we use a base instead. Use a base, it won't react with the acid or with the metal, and so it'll be safer. Okay. Okay. So we have two ways of defining these acids and bases. Okay. The first way is through the Arrhenius theory. The other is through Bronsted-Lowry theory. There's also other ones that we're not going to get into, like Lewis and acids and bases and things like that. But these are the main ones. And actually, this is the main one we're going to focus on. Okay, the Bronsted-Lowry theory of an acid and a base as to what it is defined as. So Arrhenius defined acids and bases as an acid to be a substance that dissociates to produce hydrogen. So here it is. It produces a hydrogen ion. This is hydrochloric acid. It will dissociate H plus and Cl minus. And so therefore it produces H plus ion in solution. H plus ion is the acid ion. That's the acidic ion. When we measure the pH of something, this is what we're measuring. How much of this is in the solution? Okay? That tells us what the pH is, the concentration of that H plus ion. Okay? A base was defined by Arrhenius to be something that produces hydroxide in solution. Dissociates to produce hydroxide. So the sodium and the hydroxide OH minus will dissociate. They'll come apart when you put them in water, and they will dissolve as sodium plus and OH minus. So this is a hydroxide ion. That's the basic ion. You have H plus, acid. OH minus, base. Okay? So those are the two ions that create this acid-base situation. Okay, now the problem with the Arrhenius theory of bases, not so much with acids, it's pretty straightforward with an acid, but with a base, what about NH3? Well, NH3 is basic. It's a basic ion. Or it's a basic compound. But it doesn't dissociate into OH ions, right? There's nowhere on its formula where you have OH ions. So how does it fit? So we have to expand this idea of the definition of a base so that we can put NH3 in there. Because if you measure the pH of NH3, it in fact has a basic pH above 7. So how is that if it doesn't have an OH minus ion to donate to produce into a solution? Okay, so we are going to change. We're going to change the definition. Instead of dissociating into OH minus, what we do is we say that an acid is an H plus donor. Okay, that's kind of that fits pretty well with Arrhenius theory. And a base is an H plus acceptor. So if something accepts H+, it is then considered to be a base. So the acid donates the hydrogen, the base accepts the hydrogen. So acid-base chemistry is about transfer of this H plus ion, a proton. That's what we call it, a proton. So why do we call it a proton? Well, if you consider hydrogen, it has one positive charge in its nucleus, one single proton, right? And surrounding that nucleus is one energy level that has one electron on it. That one electron is orbiting that proton. Well, if I become H plus, what happened? So how is this that I've just drawn different than H plus? What does it mean to be H plus? So right now I don't have any charge because I have an electron and one proton. They're balancing. So how did I become H plus? How does anything become positively charged? How does lithium become +1 or sodium become +1? It loses an electron. So if hydrogen loses its electron, what's left? A single proton. That's all. It's a nucleus with a single proton in it. That's it. That's all hydrogen is. H plus ions are a single proton. And they go around and they protonate things. Okay? So that's what acid-base chemistry is. The transfer of a proton. You're just passing this proton around. Something's accepting that proton. Something's donating that proton. Okay? All right. So a base in this new theory is now a proton acceptor. Something that accepts a proton. So how does that work with NH3? Well, I guess we'll get there in a second. But let's look at this now in this new theory. Okay? What donated the proton? Look at hydrogen here, Cl, HCl, and water. If I dissolve HCl in water, water is going to act as either the acid or the base. So here we can see that the hydrogen is pulled off of the chlorine. So HCl is the acid because it's donating the hydrogen. What accepted the hydrogen? Well, H2O became H3O plus. Okay? Now, if you see H plus or H3O plus, those are synonymous. They mean the exact same thing. If you have free hydrogen ion in solution, it will be in this form, H3O plus. Okay? As the hydronium ion. So you will often see it written as H plus, and you will often see it written as H3O plus. It doesn't matter. It means the exact same thing. Okay? So it's just that I could write these differently. If I show the water in the reaction, I have to write H3O plus. If I just say HCl dissociates into H plus plus Cl minus, then I don't include the water. Okay? And I don't say H3O plus. That's really the difference. Did you include water in the reaction or not? Okay? Or did you just simply assume it to be there? Okay? So this is the acid because it donates the hydrogen. What is the proton acceptor? Water, because it became H3O plus. It picked up that hydrogen, right? So water's the base. What's the acid? HCl. Okay? Now look at NH3. If I put NH3 in water, it's going to make a basic pH, meaning that there will be hydroxide ion produced, OH minus. Okay? How? Well, NH3 is a base, which means it's a what? It's a hydrogen a proton acceptor. It accepts hydrogen ions. Where did the hydrogen ion come from? It came from the water. If I take hydrogen away from water, what's left? Hydroxide. Okay? So this donated its hydrogen to ammonia, and then I get NH4 plus and OH minus left over. So now I have the basic ion OH minus in solution, and therefore my solution is basic, has a basic pH. Okay? Okay, so NH3 did what? It accepted a proton, therefore it is a base. Water is the acid because it donated the hydrogen, the proton. Okay? So as you can see, water possesses both properties of acids and bases depending on what you're reacting it with. If you react water with an acid, water will act as a base. If you react water with a base, it will act as an acid. Okay? Okay, conjugate acids and bases. So we saw NH3, the NH3 reaction, NH3 plus H2O to produce NH4 plus OH minus. Okay? So here I have a base. Here I have a reversible reaction, meaning this creates an equilibrium. Remember how we talked about equilibriums? So that hydrogen is going to go on to NH3 and then come off of it. And then go back on, and then come off, and then go back on in equilibrium. It's a reversible reaction. Okay? So when that hydrogen is off of it, it's NH3. When it comes onto NH3, it becomes what? It becomes NH4 plus ammonium. And ammonium is related to NH3, right? So here, these guys are the same except for that one hydrogen that keeps coming on and off. They're going back and forth in equilibrium. So I create NH4 plus from NH3 simply by that hydrogen coming on and off, on and off, on and off. Okay? In equilibrium. So it's in equilibrium, and it's doing that. So I would say NH3 is a base because it accepts a hydrogen. How would I describe NH4, though? Does it accept hydrogens? No. What does it do? If it goes from NH4 to NH3, what do we say that? What is it doing? It's losing that hydrogen, right? It's donating. So how would I describe it? As an acid or a base? What? An acid. Good. This is an acid. What is this? This is a base. So this is the base. This is the acid. Look at the general form. The acid is the thing that has more hydrogens. It becomes, by losing a hydrogen, a base. Because now it can accept a hydrogen and go back. Okay? So the acid has more hydrogens, just like here. Which one has more hydrogens? NH4 plus. It's the acid. Of this acid-base pair, this has more hydrogens, therefore it's the acid. This has less hydrogens, therefore it's the base. Okay? Now we say that this is a conjugate acid-base pair. It's the conjugate because it was created from NH3. I can't go from NH3 to acetic acid. No, I have to go to ammonium because that's the conjugate of NH3. That's what ammonium becomes when it picks up a hydrogen. And what does ammonium become when it loses a hydrogen? It becomes ammonia. Okay? So these are the conjugate acid-base pairs. They're related to one another. just simply by that hydrogen coming on and off, on and off. Okay? They're conjugates. This becomes that. That becomes this. Okay? And here, same thing. This is the base, and it becomes this acid. This is an acid. This is a base. Okay? And they go back and forth. Back and forth in equilibrium. These are the conjugate acid-base pairs. Okay? We can only have that if we have a reversible arrow. HCl dissociates into H plus Cl minus. There is no double arrow there. We don't write HCl with a double arrow because it doesn't go back and forth. It doesn't have a reversible reaction, equilibrium reaction. It just goes one way. This way. That's it. One way. It dissociates 100% of its hydrogen ions and does not pick them back up. But these acids that have an equilibrium, they don't dissociate 100% of their hydrogen ions. It goes back and forth in equilibrium. Okay? Okay, so you can see this is the conjugate acid-base pair. This is the base-acid pair. Okay? Those are the conjugates. Okay. Yes. All right, degree of dissociation is simply a way for us to look at how much of a hydrogen ion comes off of an acid or vice versa. Okay? So the degree of dissociation of hydrogen, if it's a strong electrolyte, which means it's a strong acid, it's 100% dissociation. It comes off 100%. If it's a weak acid or a weak electrolyte, let's see here. Okay? It's only partially, a small percentage dissociates. Okay? And we consider it to be a weak electrolyte or a weak acid. So if it's an acid and it's a weak electrolyte, it's a weak acid because it doesn't dissociate the hydrogen 100%. It comes on and off. There's an equilibrium being established. Okay? But if it's a strong acid, that dissociates 100%. That's a strong electrolyte. It will conduct electricity very well in that situation. Okay? These are strong acids and strong bases. All right? They dissociate 100%. See the single arrow? That indicates 100% dissociation. It only goes one way. This reaction goes one way. There's no reverse to it. Okay, so here's some examples of some strong acids and some strong bases. These halogens create strong acids and bases: hydrochloric acid, hydrobromic acid, hydroiodic acid. Okay, nitric acid, sulfuric acid, perchloric acid. Those are strong acids, and it has to do with the fact that some have higher hydrogen ion concentration than others. Okay? So here, look at the ratio between oxygen and hydrogen. It's a big ratio. Big difference, in other words. There's a lot of oxygens, very few hydrogens. That means that hydrogen is going to come off very easily. A lot of oxygens, few hydrogens. The first hydrogen comes off very easily, the second one does not. So the first hydrogen is a strong acid step, the second hydrogen is a weak acid step. Okay, but most of the concentration of hydrosulfuric acid is mostly dependent on the first hydrogen ion, because it's the strong acid step. Lots of oxygen, one hydrogen, strong acid. Okay. Now, if I go to HNO2, all of a sudden it becomes a weak acid, because those oxygens aren't pulling away from that hydrogen strong enough to allow it to fall off in a strong acid step anymore. Okay, so looking at the oxygen-hydrogen ratio will tell you a lot of times whether it's going to be a strong acid or a weak acid. All right, and then halogen acids are usually strong acids, except for the one you don't see up there is HF. That's because HF is a weak acid. Weak. It's not a strong acid. So it's not in this list. This is the only halogen that's not a strong acid. The other HCl, HBr, HI, those are strong acids. Okay? Okay, so here we have some weak acids, like acetic acid and carbonic acid. So yes, they're called weak acids, but you shouldn't make fun of them just because they're weak acids. Okay? It's not nice. All right? These guys are really important because they do important jobs. In fact, they do more important jobs than the strong acids a lot of times. The strong acids, they just dissociate 100%. They're done, right? Lots of hydrogen ion. Okay? But these guys, what's important about them is they can create, if you're a weak acid or a weak base, you can create something called a buffer. And buffer systems are super important. This one, super important. Yeah, I guarantee you care about this one because that's the buffering system of your blood. Okay? Without it, you'd be dead. You eat some candy, just some sour candy, right? Your pH you're changing the pH of your blood, or you would, okay, if you didn't have a buffering system, because you're adding all that acid to, you're dissolving it all, a bunch of it into your bloodstream. But your body doesn't care. It's hey, no big deal, whatever. Okay, I have this bicarbonate buffering system. So I'm going to react that extra H plus that you just put in my blood that would kill me if I didn't get rid of it. And I'm just going to react it with the base of this buffering system and get rid of it. And my pH is maintained. 7.4, pH of 7.4. That's what you have to have in your blood. Okay? And it does that because it has this back and forth, back and forth, back and forth, back and forth. If I add acid, it reacts here and goes this way. If I add base, it reacts here with the acid and goes this way. And it pulls all that extra base and acid out and maintains the pH at 7.4 so that I don't die, so my enzymes don't dissociate and do all kinds of weird things at crazy pHs, okay? So very important. Acetic acid is another, you could create buffering systems from acetic acid also. That's vinegar, okay? You could easily create the conjugate base of acetic acid by reacting it with baking soda, and then you'll create some sodium acetate. You could boil away all the water after that, and you'd have a white powder of sodium acetate. You then could take some vinegar, put some sodium acetate in it, and you would create a buffering system. You test it against pH. The pH will be maintained. It will stay constant. Okay? You're not going to be able to change it because it's buffering those changes. It's buffering it out. Here's some weak bases. Ammonia is a weak base because it has an equilibrium. You can create that equilibrium. Okay? These are other weak bases. Pyridine, aniline, those are weak bases. Okay? You can see here that I have one more hydrogen here than I do here. So I can easily identify this is my base, this is my acid of this conjugate acid-base pair. Okay? This is the acid, this is the base. The base is the thing that accepts the hydrogen. The acid is the thing that gives it away. Okay? So if this is going this way, it's an acid. If it's going this way, it's a base. Okay? Same thing here. This is the base, this is the acid. Look at the hydrogen, the hydrogens it's picking up here. 2, 3. Picked one up. Okay? And that's how I identify these acid-base pairs. Okay, so that would indicate a strong acid 100% dissociation because the arrow 100%, no double arrow there. Okay, so this is, I think, a really great chart because it helps us see the relationship between acid and base conjugates. Okay, so here I have HCl. It is a strong acid. Look, it's in the strong acid section, right? It goes to Cl-. Cl- is a negligible base, meaning it doesn't really have a basic property. It's not going to accept hydrogen and go back to HCl. So this is a single arrow. No double arrow. Okay? That's why these all have single arrows, because the base, the conjugate base that they produce, is not strong enough to push backwards. It will not accept hydrogens and go backwards. Okay? So it goes one way. That's it. But when you get here, look at these ones. Okay? These have acid-base properties, both of them. HSO4, SO4, 2 minus. HSO4 minus, SO4, 2 minus. This can go back and forth. We can create an equilibrium here. Okay? But look at the acid strength here. HSO4, of the weak acids, HSO4 is a pretty darn strong acid. Okay? Look, it's at the top of the list here. Look at its conjugate. What is the base strength of SO4 2 minus? It's the weakest base of the weak bases, right? This is so weak that this is almost a strong acid. So this pushes back, but very weakly. It's a very weak base going backwards. So it hardly even exists. Okay? We get here. Same thing. HF, fairly strong, weak acid. Fairly weak base. You get right in the middle. Oh, the bicarbonate buffering system. Maintains your pH at about 7.4, which is almost neutral, right? That's because these guys have almost equal strengths. And they push back and forth almost equally. Almost exactly the same, okay? Because they're right here in the middle. I get down here, look at my acid strength. It's getting weaker and weaker and weaker and weaker, okay? I get down here to HPO4 2 minus. HPO4 2 minus, no, it's hard to see. Okay, HPO4 2 minus goes to PO4 3 minus, but this is a stronger base than this is an acid. So this would be this would be stronger within this acid-base conjugate pair. Okay, the PO4 3 minus is a stronger base than this is an acid. And so this would push this way more than this would push this way. Okay? Because these acid strengths are getting close to becoming negligible. Hydroxide, negligible acid. It's not an acid. It's a base, right? So it's negligible as an acid. It's not even considered to be an acid. Okay? All right. So that's the idea behind these conjugate acid-base pairs. One's always stronger than the other. Okay? Or if they're equal, then it's neutral. They're just kind of neutralizing one another. Okay. So, identify the conjugate acid-base pair. HF, it's a weak acid. What is its conjugate? So if this is an acid, it's telling you this is an acid. The conjugate would be the what? What is the definition of an acid? An acid does what? Donates hydrogen. So what am I left with if I donate a hydrogen? F. What's the charge? Minus. Good. Okay? That's the conjugate base of HF. So if this is a weak acid and I want to know the conjugate of it, what is the conjugate base of HF? That means this is an acid. I want to know the base of it, F minus. Okay? This is also a weak acid. What is its conjugate base? Does the base have more hydrogens or less hydrogens? Which one has more, the acid or the base? The acid has more hydrogens than the base. So what is the conjugate base of H2SO4, which is an acid? HS. HS, what's the charge? Minus. That's the conjugate base. Okay? It just loses a hydrogen, right? The definition of an acid is a hydrogen donor. Okay? Sorry, I'm going to sit down. It's a hydrogen donor. So, what is the conjugate base, I guess, of this strong acid HNO3? You always become more negatively charged when you lose a hydrogen, an H plus ion. Okay? You'll become more and more and more negatively charged. Right? So because this is a strong acid, it doesn't actually have really a conjugate. Okay? I mean, if you consider NO3 to be the conjugate, it's negligible. Okay? Because it doesn't really push back. This is a strong acid, right? So you wouldn't really consider it to have a conjugate base. Okay? This is a weak base. What is its conjugate acid? A base, what is the definition of a base? An acceptor, a hydrogen acceptor. What is it going to become if it accepts a hydrogen? Okay, so the NH3 plus. Now hydrogen will be added to the amine group right there, to the nitrogen group. Okay? So it will become NH3 plus.
Is there a reason that the hydrogen gets added at the end instead of like on the H3?
Yes, the carbon will not accept any more hydrogens. The nitrogen, though, has the ability to do that, like NH3 becomes NH4 plus. So it gets added to the nitrogen group that can accept that extra hydrogen. The carbon won't do that. It won't accept anything else. Okay, so if we are looking for the conjugate base of a weak acid, we lose the hydrogen, and that's our base. These are reversible. Okay, this one is not because it's a strong acid, so it goes only one way. Okay? So it's all about how many hydrogens you have. If you gain hydrogens, what happens to your charge? It becomes less negative. If you lose a hydrogen, what happens to your charge? It becomes more negative. So it's all about becoming less or more negative. Okay? Lose hydrogen, become more negative. Gain hydrogen, become less negative. Or if you're neutral already and you gain a hydrogen, like ammonium, you become positive because you're already at 0. Okay? Okay. Water. So water reacts with itself through a self-ionization step. Okay? And it produces H0 plus and OH minus in solution in equilibrium. So it's an acid-base conjugate reaction here, going back and forth, back and forth, back and forth, back and forth. Okay? So in pure water, you have this. Now, this is a very weak electrolyte. These are not in high concentrations. Okay? They're in very, 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 very tiny concentrations. Okay? And in fact, if we look at the equilibrium constant for this, we would say that H2O plus, H2O plus H2O, and these are liquids, produces H3O plus OH minus in solution. Okay? So, if this is what I'm producing in solution, all right, what's my equilibrium? And this is an equilibrium reaction. So if I write the equilibrium expression, KEQ is equal to products over reactants. So my KEQ is equal to what on top? Concentration of H3O plus over OH minus. What goes on the bottom? What's the physical states of H2O? Liquid. Do I put them? No. They stay off, right? So all we have is that the KQ of water is equal to the concentration of H3O plus times the concentration of OH minus, because H2O liquid we don't include. So, in equilibrium, they will be in equal concentrations. Okay? I will have one that is at a concentration of 1 times 10 to the negative 7, and the other one will be in concentration of 1 times 10 to the negative 7 when it's in equilibrium. So 1 times 10 to the negative 7 times 1 times 10 to the negative 7 is going to equal 1 times 10 to the negative 14. Okay, so if I put these numbers in here, and I multiply them together, I get 1 times 10 to the negative 14. So what's the significance of that? Well, we call that our KW. The KW is the equilibrium constant of water. The H plus times the OH minus equal 1 times 10 to the negative 14. So what if my H plus was something other than 1 times 10 to the negative 7? What if it was 1 times 10 to the negative 5? Could I figure out what the OH minus concentration is? Yeah. OH minus concentration is equal to 1 times 10 to the negative 14 divided by 1 times 10 to the negative 5. Okay? Because this stays constant. 1 times 10 to the negative 14 does not change. What changes? These can change, but this remains constant. So if my OH minus and my H plus are the same concentration of 1 times 10 to the negative 7, then that solution is a neutral solution. Pure water would have these at 1 times 10 to the negative 7 each. And it would be a neutral water solution. But if my pH becomes acidic, that means I changed this. So if this goes up, this must come down so that I can maintain this equilibrium constant of 1 times 10 to the negative 14. Okay? To maintain 1 times 10 to the negative 14, these have to fluctuate. Up or down, up or down. Okay? And they will always be in opposite directions of one another to maintain that concentration or that equilibrium constant, 1 times 10 to the negative 14. So this is how pH works. H plus and OH minus go hand in hand. If one of them increases, the other one decreases. If one of them, if the other one increases, the other one will decrease. Okay? So that 1 times 10 to the negative 14 can always be maintained. And that's how we get our pH scale. So the pH scale, pH is a measure of the H plus ion concentration. pH equals the negative of the log of the H plus ion concentration. So if my H plus ion concentration is 1 times 10 to the negative 7, where's the log? What is the logarithm of this number? Negative 7 is the log. So if my pH is equal to the negative log of 1 times 10 to the negative 7, then what is the negative of negative 7? Positive 7. So my pH is equal to 7. Because if H plus is 1 times 10 to the negative 7, then H3OH minus is also equal to 1 times 10 to the negative 7. So if the pH is 7, the negative log of the H plus ion concentration is 7, then the pOH is also equal to 7. The negative log of the OH minus ion concentration, negative 7. The negative of a negative 7 is 7. So my pOH is 7. What if my H plus ion concentration is equal to 1 times 10 to the negative 5? What is the pH? 5. What is the OH minus ion concentration? Okay, let's start here. So if my KW is equal to 1 times 10 to the negative 14, okay? If I take the negative of the log of the KW, what does that equal? 14. 14 equals pH plus pOH. If my pOH is 7 and my pH is 7, that equals 14, right? If my pH is 5, my pOH is what? Nine. So what's the HOH minus ion concentration equal to? If my pOH is 9, then my OH minus is what? Well, my pH is 5. My H plus ion concentration is 1 times 10 to the negative 5. So what's my OH minus ion concentration? 1 times 10 to the negative 9. Because they have to be in equilibrium. They have to maintain. So if I take 1 times 10 to the negative 9 and multiply it by 1 times 10 to the negative 5, it's going to equal 1 times 10 to the negative 14. Just like pH plus pOH has to equal 14. 5 plus 9 is 14. Okay? So hopefully you're starting to begin to develop this idea of how this pH and H plus ion concentrations and everything are related. Okay? So, the pH scale tells us the concentration then of the H plus ion concentration. It tells us how much H plus there is in solution and whether we have more of it than OH minus. So if my pH, let's say, my pH is equal to 10, what is my pOH? 4. This is a basic solution, right? If pH is 10, it's basic. Why? Because this is in a greater concentration than this. This is equal to 1 times 10 to the negative 10 H plus, right? This is equal to 1 times 10 to the negative 4 OH minus. which is a bigger number? This is in scientific notation. This is in long, if I write it out in longhand, okay? So what do you notice? Which one's more concentrated? This is a lot more concentrated, right? This is a bigger number than this. This is a super tiny number. So if my pH is 10, that means I have a very small concentration of H plus ion. If my pH is 14, I hardly have any. That's 1 times 10 to the negative 14, H plus. If my pH is 1, that means I have a lot more H plus ion concentration than these other pHs. Okay? So, as my pH decreases, what's happening to the ion concentration? It's increasing. As my pH decreases and the H plus ion concentration is increasing, what's happening to the OH minus ion concentration? It's decreasing. But as my pH increases, 10, 11, 12, the H plus ion concentration is decreasing, and the OH ion concentration is increasing in solution. Okay, it's becoming greater. Okay, so we've seen that those two are in equilibrium with one another. Okay, yes, that's how we can measure. Okay, so here pH is equal to the negative log of the H0 plus. That's the equation. POH is the same. POH is equal to the negative log of the OH minus ion concentration. Okay, so what is the pH of a 1 times 10 negative 4 molar HCl solution? So the clue here is this. HCl. This HCl dissociates into H plus Cl minus in a strong acid step. This is a strong acid, and therefore it dissociates 100%. So if my acid starts out at 1 times 10 to the negative 4 HCl, it dissociates into 1 times 10 to the negative 4 H plus and 1 times 10 to the negative 4 Cl minus. So if I want to figure out the pH of this, I just simply need to look at what this is. The H plus ion concentration is 1 times 10 to the negative 4. What is the pH? Somebody said it. 4. pH is 4. Okay, because my log of this is negative 4. So the pH is 4. Good. What is the H0 plus ion concentration that has a pH of 6? One times 10 to the negative 6, right? Okay, now, if my pHs are whole numbers like this, it's super easy. 1 times 10 to the negative 3, 1 times 10 to the negative 2, 1 times 10 to the negative 10, 1 times 10 to the negative 11. But what happens when I have a pH equal to 3.65? It's not the same, right? Well, it is. It's just that you can't report it as the same. You can't report it as 1 times 10 to the negative 3.65, although that's correct. You need to calculate it. So you need to do that calculation to figure out what the H plus ion concentration equals the H plus ion concentration. Okay? So you have to use a fancy little button on your calculator called the anti-log. It's usually a shift function of log. LOG, log. If you find the anti-log, you usually hit shift log and it says 10 to the x. And you would enter it in your calculator as 10 to the negative 3.65. Okay? And that would tell you what the H plus ion concentration of a solution is that has a pH of 3.65. Okay, somebody find it? Did you guys find that button, H 10 to the X?
I got 0.00223872.
0, 0,
0.
0.
223872.
Okay, so 2.24, let's say, times 10 to the negative 4. Okay? So now, with that answer, what I want you to do is find the negative log, or just simply what is the log, what is log of 2.24 times 10 to the negative 4? What is the log of this number? What'd you get? Okay, now drop the negative because we're going to take the negative of the log, and it's 3.65. You can go back and forth, right? Easy, easy, easy. This is what I have my kids do when they're like, Dad, I'm bored. Okay, log, anti-log, log, anti. Okay, so you could go back and forth all day between those two, right? Log, anti-log, log, anti-log. All right, and you would just keep getting those same answers. All right, so this is how we can go back and forth between pH and the H plus ion concentration, or between POH and OH minus ion concentrations. Log, anti-log, back and forth, okay? All right. pH of a base. So here is the concentration of KOH. KOH has a concentration of 1 times 10 to the negative 3 molar. So what is the POH? Excuse me. Well, this KOH is going to dissociate into K plus OH minus in a strong base step. So if it's 1 times 10 to the negative 3 molar KOH, that means it becomes 1 times 10 to the negative 3 K plus and 1 times 10 to the negative 3 OH minus. So what is the POH then? Three. The POH is 3. Okay? So when it's 1 times 10 to the, it's easy to see, right? It's 3. When it's 2.56 times 10 to the negative 3, then we have to calculate it, all right? But if it's just these whole numbers, we can easily see what the log is. It's negative 3. We can figure that out, okay? All right, now, so if my POH is equal to 3, what's my pH? So this has a pH of 11. It has a high concentration of OH minus, 1 times 10 to the negative 3, and a low concentration of H plus, 1 times 10 to the negative 11. Okay? So this is a basic solution. It's a basic solution. Okay, so here they're showing that, right? So we get to pH of 11 because, okay, they did it differently. They went to the H plus concentration from here because they said 1 times 10 to the negative 14 is equal to 1 times 10 to the negative 3 x. And x is the H plus ion concentration. So 1 times 10 to the negative 14 divided by 1 times 10 to the negative 3 is equal to 1 times 10 to the negative 11. And then I can take the negative log of negative 11, and pH is equal to negative 11. Okay? Because this is my OH, this is my H plus. Okay? Okay. So there's always two ways to find any of these things. To find your pH or to find your OH minus, there's always two ways. If you have one starting point, you can go and you're trying to find something else, you can always do it in two ways. Okay? So a lot of times you'll see that, and it doesn't matter which way you go. What is the OH minus ions of a solution with a pH of 5? Okay? They're doing it one way, but I think that this way would be easier. What is the pOH? If the pH is, the pH is 5, what's the pOH? 9. What's the OH minus ion concentration then? 1 times 10 to the negative 9. Okay? We did it one way. They did it a different way. They found the H3O plus because it goes to 1 times 10 to the negative 5, right? 1 times 10 to the negative 14 divided by 1 times 10 to the negative 5 tells me the OH minus, which is 1 times 10 to the negative 9. It doesn't matter which way you do it. It will come out to be the same either way. It doesn't matter. Okay? All right, so here's some common pHs of different things. Hydrochloric acid is very acidic. Your stomach acid, right? Has to be that way to cause those enzymes to become active, the pepsinogens and those kind of things that digest food in your stomach. Lemon juice, it's acidic. It's lemon. Lemons are acidic. Lemons are acid. Lime is a base because they're kind of opposite of each other. The lemon is sour. The lime is bitter. So they have those opposite effects. Okay? Vinegar is an acid. Tomatoes are acidic. Coffee is acidic. Your urine is slightly acidic. Distilled water and blood. Well, distilled water is at 7. Blood is at 7.4. Okay, that's what they're showing us here. Can't see it that well. Okay, that's at 7.4. Baking soda. If you've ever tasted, if baking soda's ever got on your tongue, it will taste very bitter. Or, this happens to me all the time, right? So I make pancakes and I put too much baking soda in it, and they taste really bitter. It's because it's too much baking soda or something, right? So yes, it's bitter because it's a base. Oven cleaners and drain cleaners have a lot of high concentrations of sodium hydroxide. Okay, so they're corrosive. They'll get rid of all that junk. But you want to wear those big old gloves when you work with it, right? So, if you spray your oven, they say put a bunch of paper down on your floor because this happened to me. So I sprayed the oven, right, and little drips on the floor and eats right through the floor. So yeah, make sure you put your paper down. Okay. All right. Okay, so we've kind of already gone through this. You can see. This is the molarity of the acid. These are the pHs of the acid. 3, 1 times 10 negative 3. 4, 1 times 10 negative 4. The bases, pH is 10. So this is a molar concentration of OH minus at 1 times 10 negative 4 because these are in equilibrium with one another, right? Okay. Okay, so pH is important for a lot of reasons. For growing crops, you have to have the correct pHs in your soil, or else they're just not going to grow right. We talked about our blood pH. Shift of 1 pH is fatal, right? So we have to buffer that out. So we take our life in our hands every time we eat one of those sour candies. It's just full of citric acid, right? But, you know, our bodies can handle it. It's not going to, because we have that buffering system, okay? So it's not really that dangerous to us, okay? We're concerned about acids rain a lot of times because it changes the pH of stuff, like our aquatic environments. It changes the pHs of them, so it can be dangerous to the aquatic life, including the plants and things. Okay, so there's a lot of ways that we use this pH. It's important. Okay. Okay, so reactions between acids and bases. If you react an acid with a base, they will neutralize one another. Why? Why is that? Well, because H plus OH minus, this is the acid, right? This is the base. What is that going to make? H plus OH minus is going to make H2O, which is neutral. You just neutralized the acid with the base or the base with the acid because you reacted them together to form water, which has a pH of 7. It's neutral, right? So you've neutralized it. So here we have a strong acid and a strong base. The H plus and the OH minus are going to react to form water. And then you have the sodium chloride ions left over. So you take a super nasty acid, it will dissolve your hand, and a really nasty base, sodium hydroxide, which will also dissolve your hand, burn it like crazy, okay? You take these two really nasty things, you put them together, and what do they make? Are you worried about salt water? Nobody cares. Nobody's worried about that, right? Nobody's concerned about if some salt water gets on their hand. Okay? Why? Because you've neutralized those acids and bases. You've taken care of them. Okay? So disposing of acids and bases a lot of times is not a big deal because all you do is you neutralize it. You take, I do it all the time in the lab. We were working on an acid in the lab. I just grab some baking soda. It's a base. I just dump it in there until it stops reacting, and I neutralized it. Now it's ready. I can just dump it down the sink. Okay. I don't want to dump this down the sink. I'll dump this down the sink because I'll clean it out, right? Sodium hydroxide to clean out your sinks anyway, so fine. Dump some sodium hydroxide down there, clean out your sinks. But the hydrochloric acid you don't want to dump down there because somewhere down there it might run into some metal pipes and it'll start eating away at the pipes, producing hydrogen gas and things. Hydrogen gas is explosive, so when I was in graduate school, this was in the biology department. Somebody dumped some hydrochloric acid down the sink. A bad idea, right? So all this hydrogen gas is coming up out of from like the top floor, it's like 7 stories high or whatever, this building, and dumps it down there. And hydrogen gas coming out everywhere. And they close down the building. Okay, so not a good idea, right? Soda hydroxide won't do that. That's why it's safe to put it down the sink. But it's just going to neutralize itself and become salt and water. Okay, and if we look at the actual reaction that took place, the sodium and the chlorine, they just remain apart, dissolved, right? They were dissolved over here. They're dissolved over here. What do we call that? If they don't do anything, what are they called?
Spectators.
They're called spectator ions. They actually didn't do anything. They just watched hydrogen and hydroxide come together. Okay? It's just the spectators of the wedding. So they're just watching this happen. Okay? And the H plus and the OH minus form water. That's all that happened. That's the reaction. This is the net ionic reaction because the other things are spectator ions. When you react an acid with a base, this is the reaction right here. It doesn't really matter what you put here or here. Okay? An acid with a base, you're going to form H plus and OH minus reacting to form water. That's the reaction. Okay? That's the acid-base reaction. Okay, so that's the net ionic equation. Forms water. Okay? So an analytical technique to determine the concentration of acid and bases is titration. And we did a titration in the lab. You guys have done that. If you've taken the lab, you've done that. Okay? Where you take a base, sodium hydroxide, you titrate an acid like hydrochloric acid. Or we titrated vinegar as well. And you could find the concentration of either one of those because of this H plus OH minus produces water reaction. So once you neutralize all the H plus in that solution with the OH minus that you added, then you'll reach that endpoint and you'll be able to calculate the H plus ion concentration based on how much OH minus you added because it's a 1-to-1 reaction in that case. Okay? Okay, so here is the setup for a titration. You have a flask. It has an acid in it. Here you have a burette that has a base inside of it. And you will add the base to the acid until here they've added an indicator that causes it to turn pink once it's reached its equivalence point, its end point. Okay? At that point, I know my titration is done. I can calculate how much sodium hydroxide I added, and I know the concentration of this. And I know the volume, so that will tell me the moles. The moles of sodium hydroxide that I added are equal to the moles of acid that were in here, because it's a one-to-one reaction. So because they're equivalent, I can calculate the molarity of the acid through that reaction. Okay? And also, because the moles of the acid are equal to the moles of the base, and if you consider the molarity equation equals moles over liters, well, molarity times liters equals moles. If I bring this up, then molarity of the acid times the volume of the acid, which is the liters, is equal to the molarity of the base times the volume of the base if the moles of A are equal to the moles of B. And now I have an equation that simplifies how to calculate the unknown concentration of an acid or a base. Now I can simply isolate the molarity of the base here and solve for it based on the molarity and volume of the acid that I used to titrate it. Or I can calculate the molarity of the acid based on the molarity and volume of the base I used to titrate that acid. I know the volume I started with of the acid, I just don't know what the concentration of the acid was. Okay? And I will be able to calculate it using this equation. Very similar to the dilution equation. Same concept, the moles of one thing are equal to the moles of another thing. That's how we get this equation. Okay? So this, if you're given a titration question, that's the equation you want to use. You'll just simply solve for the unknown based on the volume of and molarity of the thing that you used to titrate it with. Okay? Okay, so we've kind of already gone over. You add the base to the acid, the unknown acid, until it goes pink, and then you've reached that end point, and you know that you're done. Okay? All right, we'll pick it up again there next time.